I know this is the first talk after lunch, so even I feel like taking a nap right now. So let's see. We'll try to make it less boring. I put some memes in there, so maybe it'll wake up some of us. So that's a Target. That's what we look like for somebody who's not been to a Target. This is one of the more recently remodeled Targets. It's close to where I live in Sunnyvale, California. Target is been around for a long time, 70 odd years in its current form, and for more than 100 years. And if you track the lineage of all the companies that folded into Target, we have stores in all the states, more than 350,000, maybe 400,000 team members, over $100 billion in annual revenue, omnichannel shopping, so stores and online. And what's a little bit unique about Target is that our stores and online businesses are run together, as opposed to other retailers that might run these as separate businesses, or some other retailers that might be only online, and so on. We focus on pretty much all categories: home, hard lines, essentials, beauty, apparel, grocery, so wide variety of categories. There are two more pictures there, one of the inside of a store, one of a larger Target. Our goal is to really help all families discover the joy of everyday life. So when you go to a Target store, it's usually well lit, spacious, well designed. This is not by accident, it's intentional. People in data sciences tend to think that data science is the most important thing in the world, but when you're a shopper, you want a nicely decorated store. You don't care much for data science at that point. As for myself, I'm Subramanian Iyer, I go by as Subu, Senior Director of Data Science at Target. Ex-Google, ex-Goldman Sachs. I've been doing AI before AI was cool, I guess. I heard that line from earlier today. I think I'm going to steal that line. My teams work on forecasting. So in this talk, we'll take a look at one cross-functional challenge and how we dealt with that challenge using AI. Specifically, it's a case study of using machine learning for forecasting demand in retail. Several key learnings from that experience, and then some technical insights. I've tried to make the talk quite accessible, not very technical. At the same time, tried to distill some of our insights and learnings from many years of working on this. So let's get into it. So first thing is pick the right problem to get started. You have to know where you're starting before you can go out on your journey. Retail is very rich with all kinds of problems. So there's a cartoon diagram to what is retail. There's a factory on the left. You are purchasing from that factory that lands up in a distribution center. It could be your own factory, it could be somebody else's factory. From the distribution center, stores are replenished on a fairly regular basis. You could also replenish fulfillment centers. Fulfillment centers tend to be places from where orders are fulfilled, online orders are fulfilled. And then at the very right of that image, you have demand itself, and the demand could be materializing either online or in store. If the demand materializes online, the shopper could be selecting a store from where they would pick up the item, or they could be saying, just send it to my house. So you have different modalities of shopping and different ways of fulfilling that, and all of the echelons of the supply chain that you have to get right in order to do that. So when we talk about demand forecasting in retail, you could conceptually think about forecasting at every single one of these, right? The goal really is to say, let's provide accurate forecasts at each location for each item to meet daily demand of all of the guests that will shop at those locations. And the goal is really to maintain sufficient inventory, but not too much inventory, because otherwise your chief financial officer gets upset, because you have spend all your money filling up the back room and stuff is not selling, right? So there's that trade-off. So what is the problem we're going to pick? So let's look at that. So let's look at demand forecast a little bit more. You have various retail processes now. You have, as I touched on earlier, purchasing, inventory allocation, positioning, pricing items. You have to plan labor at the stores, at distribution centers. How many trucks do you need? How many truck drivers do you need? So on and so forth. All of those are in some sense planning problems. So from an OR perspective, you have planning and then you have control. So a number of these problems are planning problems. And then you have control problems, right? So you have, or rather, those are all control problems. And then you have various planning problems. When should we manufacture? What items should we carry? How should we think about finances? How do we allocate budgets? All kinds of operational issues that have to be planned many years in advance. If you're going to remodel a store, then you need to buy the shelves that will go into that store, and those shelves need to be manufactured by somebody else, and you need to do that ahead of time. So there's a sequencing problem that's involved. So you need forecasts to drive pretty much all of these decisions. Where do we start? So let's say we start with the supply chain, because the supply chain is usually the more granular forecast. It involves more of the control rather than planning problems. So it's a good place to start because it's usually easier to work with short-term control problems. Supply chain operates at enormous scale. Here is an illustration of the scale as well as the type of algorithms needed in supply chain. So network planning, where should your stores, distribution centers, whatsoever, where do all of these need to be? How are you going to position the inventory? How much inventory do you need? How are you going to place the inventory? How do you think about transportation? And then the actual control problems associated with transportation, which could be a traveling salesman's problem or a vehicle routing problem, something of that nature. So there is predictive analytics, there's traditional operations research, there's all kinds of graph algorithms, there's a bunch of stuff that goes into operating the supply chain, right? That's an indication of target scale. So roughly 200,000 items at each store. Of the order of 2,000 stores, right? 365 days in a year. You might want forecasts for a couple of years. You might have multiple scenarios, so adjustments to prices, adjustments to your assortment, all of those would require reforecasting. So if you just naively multiply all these numbers together, you have trillions of combination of forecasts that need to be generated. So is it even possible to generate these forecasts? Is it realistic to generate all these forecasts? How will we use these forecasts to solve all of the problems that we talked about earlier? That's the journey we set out on many years ago, and we'll get to that. So second principle is don't boil the ocean, start small. Pick one of those problems and work on it, right? So the modern capability we want is omnichannel forecasting. You want to be able to do store pickup, in-store shopping, sending Shipt or Instacart to go buy it for you. You also want to be able to say, ship it to my house from the store. I've called that the store replenishment problem. So that's where we started. We said we'll worry about what inventory needs to go from a warehouse to a store and when should it go. And from there, we'll expand to the other problems. So let's look at store replenishment a little bit. So here are some objectives. So the first one is when you go to the store, there needs to be availability. Otherwise, you're unhappy. The second one is you don't want too much inventory cluttering the back rooms, because if there's too much inventory, then the store employees can't find items. It's a trip hazard. There's all kinds of problems that happen. And then the third one is, of course, when you walk into a Target, it has to be beautiful. Otherwise, you're not going to walk into a Target, right? Stores have to be beautiful. That means you can't have overcrowded front of the stores either. So these things pull in somewhat different directions, as you can imagine. Like you can say, I will never be out of stock. I just need to send practically infinite inventory to the store. But then you're either going to have cluttered back rooms or you're going to have cluttered stores themselves. So that brings us to the next insight we had was that you should divide the problem into smaller pieces. So in this case, how do we divide the problem into smaller pieces? So we looked at it and we said, for a retailer that operates a large format store, a good chunk of replenishable items. So not every item is replenishable. So if you think about replenishable items, a good chunk of them sell very few units. If there is a table lamp, that's not going to sell 10 units a day per store, right? It's not going to be a massive fast seller. It's going to sell a few units a week, or even less than a unit a week, right? So these are slow sellers. Bananas, on the other hand, you're not going to sell one banana a week. You're going to sell hundreds of bananas every day at every store, right? So you have to differentiate between these slow and fast-selling items. So what does that mean for us? So this picture kind of shows here on the left side, every dot in this picture is a representation of a forecast of an item at a store. So on the left side, you have slow-selling items. So the x-axis is sales velocity. The units don't really matter. This is just illustrative in nature. On the left side, you have slow sellers. On the right side, you have fast sellers. So for the slow sellers, you have a lot of variance because you don't know. This store could be selling 0. Another store could be selling 3 this week and 0 next week. For the fast sellers, you have a lot less variance. So your forecast can actually be fairly accurate, right? So for the fast sellers, you want to focus on good store forecasts because that black line is your mean forecast across your stores, right? That's your average forecast. For the slow sellers, you want to focus on keeping shelves full and you want to focus on whatever you need to present in the store. You want to make sure that the store looks good, right? So what is good? We need to have a definition for what does good mean in order to develop our forecasting models. So what good means is, technically it's variance and bias, right? So fundamentally what this means is if you have a forecast, if you have sales, then you want your forecast band to be very close to the sales. So that's very tight. And you want your forecast band to be even around the sales. So you don't want to over forecast massively, nor do you want to under forecast massively, right? If you over forecast, then you're going to run into one type of problem where you send more inventory to the store. If you under forecast, then you're going to run into the opposite problem where you have too little inventory in the store and then you run out of stock, right? So you need to have a notion of what is good, and inversely that means you have a notion of what is bad and what are the implications of being bad. So in this case, it's asymmetric. Being bad on the over forecast side is very different from being bad on the under forecast side. And again, this only applies to the fast sellers because that's the only place where we care about store level forecast accuracy. So having said what is good, now the next thing is, if I generate a forecast and give it to you and say, send this much inventory to the store, will you trust it, right? And more often than not, in large retail organizations that have been around for a long time, the answer is no. I would not trust it because I have been operating very well for all these years. Thank you very much. Who are you to come in and say, I will give you a brand new way of forecasting, right? So this has to be explainable. The forecasts have to be good, but the forecasts also have to be explainable. It's very hard to trust a black box. In general, we know that regression models are more explainable than deep learning models. So what does that mean for us? Like regression models are often not accurate enough. So what can we do about that? Right? So we start with a linear regression. I promise this is probably the only technical slide here. So we start with a linear regression. That's y is the forecast, and all the x's are the various features that go into the forecast. You can change that. You can transform the output. You can stick a function g in front of the y. So now you have picked up a generalized linear model, right? So you have basically said, I'm going to pick my y from an exponential family. And then you can add various unit-specific effects. So this is now the alpha j there is now a normal variable that represents various unit-specific effects that go into the forecast of the item. So this is just to say I'm going to forecast a bunch of items together, and then each item is going to get its own effect. So now this is a mixed model, GAM, and then you can also transform various inputs. You don't need all of your inputs to be linear. So those transformations will give you a generalized additive mixed model. So if you look at the form of the generalized additive mixed model, GAMM, you see that it's still linear. So it's still fairly explainable. It's definitely less explainable than a regression because that function f1, let's say it's a cubic, it's not going to be as explainable as if it were linear, but it's still pretty darn explainable. So the next principle is what is truly important. So let's say we settle on this model form where we say we will use generalized additive mixed models. So what is truly important? So from a forecast perspective, what is important is being able to explain in terms of what is the base forecast, right? There are only so many toothbrushes that you can sell in any geography. You can't sell 100 times that many toothbrushes in that geography. There just aren't enough people. Right? There are calendar factors. Spiral-bound notebooks sell a lot when it's time to go back to school or college, right? There are various internal and external factors, right? So a celebrity tweeting something would be an external factor, which you have no control over. An internal factor might be running a promotion. And Target in particular is a retailer that runs promotions, right? And then you have all kinds of reactive factors. These are recent activities. They are very hard to predict ahead of time. So what do you do about this, right? So the key design choice we made was we said we'll identify the main predictive factors and we will include those in the model. And then the reactive factors we'll include it in our system. We won't even try to forecast them or we won't even try to predict them. There's more dimensions there. There's a bunch of stuff on that slide. I'm not going to read everything. The next big question we had to think about was what is the right level of aggregation for forecasting? So the level of consumption, we just said, is every item at every store every week to determine what to send to the store. But you don't necessarily have to forecast at that aggregation. You could forecast at a different level of aggregation and then have the AI algorithms identify how to get you the forecast at a different level. So you could have a hierarchical model, for instance. So that is the form of the forecasting algorithm that we then had, or we have, which is you have an intercept. This is the average weekly sales per store in the group of stores, right? You have a store-specific effect. You have various effects based on calendar, so seasonality, there's elasticity to price changes, you have various holidays and so on and so forth, right? So that's the explainable and reactive forecasting model that we settled on. So I'll get to some technical learnings now, right? So we tried various other things, okay? So we tried neural networks, we tried state space, Kalman filters, exponential smoothing, all kinds of ARIMA, like the entire zoo of things there, random forest, gradient boosting, bottoms up, top down, pretty much we tried a lot of different things. And the most amazing thing we found was that every single model was better than all of the others. All you had to do was tweak the test or validation data, and then you'd have a different model that was better. So what we realized was that the complexity of the model or the distinction between the models wasn't what was important. What was important was, can we explain it, and can we get a unified framework that does most of what we want? The next thing we realized was, we are building millions of models, hundreds of millions of models. It's critical to pick something that's flexible, right? Otherwise, we will end up with too many model classes. It's practically impossible to support all of that from a production perspective. It's impossible to scale that and get everything working all the time. The next one, so you don't just measure accuracy. There are many different measures of accuracy. MSE, MAPE, weighted MAPE, mean absolute error, all kinds of stuff can happen. Goals are often arbitrary. Your business might come to you and say, give me less than 10% MAPE, give me less than 5% MAPE. I mean, I would love to have a crystal ball that gave me 0% MAPE. Like, I want to predict the future exactly. That's not doable, right? So the thing to ask is, what does the business problem that I'm trying to solve, what does it actually need? If you're selling one item every 2 weeks, then that forecast is 1/14, it's 0.07. What does a MAPE of 50% even mean? How is it going to matter if your forecast is 0.07 or 0.10? You can't send a fractional unit to the store anyway, right? And then this is another one. The accuracy, so this was the image that I showed earlier. I showed that in the context of fast sellers and slow sellers, but the same idea applies at pretty much every level. Instead of number of items or the volume of items being sold, you could have different aggregation levels. So if you tried to forecast at the level of all 1,900 stores at Target, you could get a much more accurate forecast than if you were to try and forecast every single store, right? So as the data becomes more granular, you pick up a lot of noise, and all machine learning algorithms will pick up these noise. So you have to think about, how am I going to handle this noise? How am I going to deal with anomalies, stockouts, missing data, bad data, new items, things that you cannot estimate, so on and so forth. Where can we borrow information to solve for some of this? And then finally, in terms of technical insights, we realized that you have to constantly be asking, am I forecasting the right thing? You could easily be forecasting the wrong thing. Maybe you should be forecasting dollars and not the number of units you will sell. Maybe you should be forecasting packages. If that is what your process needs, if you're going to think about how many trucks do I need, then maybe you should be forecasting packages rather than dollars or units. This fundamentally means that all of our data scientists have to have a nuanced understanding of how the business operates. All of these data scientists are first and foremost retailers, and secondarily statisticians. So the statistics is important, but being able to have a grasp of what the business is much more important. Okay, let's get to some engineering. So another thing we realized fairly early on was that modular architecture is critical. So software engineers know this very well. Machine learning and statisticians typically don't understand this concept too well until it's pointed out to them. It's a fairly obvious point. You say that instead of thinking of it as one model, think of it as a collection of models. It's as simple as that. But fundamentally, that is a phase shift in how you think about this. You think about the world as a portfolio of things that you're trying to optimize rather than one single thing that you're trying to do. So what does that give us? So if you look at forecasts, so these are a plethora of business processes. I touched on some of these in an earlier slide at the beginning. Here are different types of forecasts that you might want for those business processes. So inventory planning and the unit forecast at the stores is what we have been talking about, but you could have warehouse forecasts, you could have forecasts for sales channels, you could have all kinds of stuff. When you start thinking about it as modules, when you start thinking about it in terms of a collection of models, now you start thinking about each individual effect differently. You start thinking about it as a collection of, as a set of building blocks, which you then assemble into the forecast. That's a very powerful way of thinking about coherence across your various business problems. ML engineering. So this is the age-old problem. There's all kinds of stuff that needs to happen after the machine learning work is done and after you think the models are ready. Because traditional programming is about humans writing the code that will produce the results. Machine learning is actually giving you the code, it's giving you the model, and then that has to be then executed. Yes, you could have programs that write programs, but we won't get into that, right? As we thought about what is important from an engineering perspective, there are three hierarchies here. So there is software, there's models, and then there's forecasts. And each of those need to have certain properties that are useful or that are fundamentally required in order to make good solutions. And I've listed them there. I'm not going to read them all out. The last key principle I want to touch on is to think about data science as a product as opposed to a project. A project is something that you do once, and then it has a short life cycle, and then you get done with it and you move on. A product is something that evolves over time. It continues to persist. You create the model, you put it into production, and then you have to learn, you have to intervene, you have to monitor, and then once you monitor, you recognize that it's going off track, and then so you have to go back into the discovery process, and you have to keep caring for the model. The care and feeding is very critical. That is that evolution from thinking about a portfolio of projects to a product that evolves over a period of time has been critical for our ability to think about creating coherent forecasts that cut across supply chain, merchandising, finance, operations, stores, and so on and so forth. There's a bunch of other stuff that I have on here. There are all kinds of requirements, exogenous events, we talked about some of them, back to school, pricing, so on and so forth. You might have fallback models that are needed. Your models need to be stable. You have to track and maintain them. There will always be manual overrides. People will want to know, when should I trust the model? When do I not trust the model? When I don't trust the model, what do I do about it? Are there emergency procedures for that? So on and so forth. In summary, if we were to do this all over again, we'd try to make a smaller mess. We learned a lot by failing on a lot of things. This is a speaker earlier today at the keynote who said that she's learned a lot by failing for 13 years, and it certainly feels the same way. We have succeeded by trying every single thing that could go wrong and figuring out how to fix it after it went wrong. There's a couple of papers you can look at if you want to get more details. So the first paper is the one that, for the most part, I've presented in this talk. The other paper is a couple years older. That has more technical details as of the time the paper was written. Thank you for attending.